What's up, Raiders? Just going to continue our discussion of some one-dimensional motion problems. So picking up where we left off, here's number 16. A parked car with a broken emergency brake gently rolls off, initial velocity 0, a cliff. How long does it take to reach 80 kilometers per hour? So right off the bat, we don't want to have a situation with mixed units since we know we work with acceleration of gravity in meters per second squared. So we'll convert this final velocity of 80 kilometers per hour to meters per second. So we'll take care of that first. And remember, per hour, that basically is your division bar, 80 kilometers per 1 hour. So I'm not going to explain this part too much because we've done this in multiple other problems. So 80 kilometers per hour is approximately 22.2 meters per second. And if we look at the wording of our problem, the parked car with a broken emergency brake gently rolls off. And in this case, you need to infer from the fact that it gently rolls off that the intention here, and it's put in parentheses, is that the initial velocity it's going to drop off with is 0. And then how long does it take to reach 80 kilometers per hour? Well, this is the whole thing we've talked about. The entire time it's in free fall in the air, gravity's accelerating it. So that approximate equivalent velocity of 22.2 meters per second that we're looking for, that's not velocity because the velocity is changing over time, that'll be final velocity. So in terms of identifying what we're given and what we're trying to find, in terms of our equation variables, we know the initial velocity is 0. Acceleration caused by gravity pulling down is negative 9.8 meters per second squared. Final velocity is approximately 22.2 meters per second, and we're trying to find time. So if you look at your list of equations, this specific combination of variables can be combined with VF equals VI plus AT. So substituting our values in, 22.2 for the final velocity is approximately equal to, now the initial velocity is 0, that term goes away. So negative 9.8 t. Now I want to point something out here. Velocity, acceleration, displacement, those are all vector quantities, so direction matters. So the acceleration of gravity pulling down, if we stuck with the convention of up is positive, down is negative, that's negative. Now the final velocity, we have the quantity 22.2 meters per second, but to be consistent with signs, that's on the way down. So we're going to manually add in a negative sign ourselves here to be consistent with directions. So now divide both sides by negative 9.8. So the time that it takes for this car to hit the ground is about 2.27 seconds. Okay, moving on. A stone is dropped from the top of a cliff. It is seen to hit the ground below after 3.8 seconds. How high is the cliff? So this problem, while it's not a car, it's just a stone. In reality, it's the same scenario as the problem we just did, because notice it says a stone is dropped. So from that, we can reasonably infer the initial velocity is 0. So given information, initial velocity is 0. Acceleration of gravity pulling down is negative 9.8 meters per second squared. And now in this case, we do know the time, unlike the last problem, 3.8 seconds. And then how high is the cliff? Well, in terms of our equation variables, that's displacement. So same scenario, just a different combination of variables, and we're looking for something a little bit different. So in this case here, this specific combination can be related to each other with d equals VIT plus 1/2 AT squared. Now we've already done some more elaborate problems using the quadratic here, but in this case it'll clean up pretty neatly. Since the initial velocity is 0, this term goes away. So the displacement is going to be 1/2 times the acceleration of negative 9.8 times the time squared of 3.8. So we're going to get here approximately negative 70.8 meters. And again, displacement's a variable, a vector, so that means direction matters. So basically what this is saying is the stone's going to end up 70.8 meters below where it started. It was dropped, so that makes sense. But in terms of the wording of our question, how high is the cliff? Well, when you're talking about height, that's not a vector quantity. So we would just say then that the height is approximately 70.8 meters. And at that point, we can drop the negative sign because height we don't measure in terms of, we don't describe it with a negative value. Okay, moving on. If you take a look at 18, a foul ball is hit straight up in the air with a speed of about 25 meters per second. Part A, how much higher does it go above the bat that hit it? How long does it take the ball to reach its peak? So this is an example of a problem where, because it goes up and does come down, you can break this apart multiple ways. Depending on what's being asked, you can analyze the entire trip. You can just focus on the way up to the peak. And in this case, since both the things we're looking for are focusing on the peak, we're just going to analyze up to the peak. And because this motion's more complex than the previous two problems, in the previous two problems, you only had an object moving in one direction. But now that we're talking about a ball going up and down, now, because it can be analyzed a variety of ways, it's important that for yourself, you identify what segment of the problem you're focusing on and that you declare it to me as well. All right, Mr. Dubois, all these calculations here are just going to focus on up to the peak. So our given information, the initial velocity is 25 meters per second. And while it's on the way up, gravity's still pulling down on it. It's still in free fall, even on the way up. So being consistent with signs, since these are vectors, direction matters. The initial velocity up is positive. Acceleration from gravity pulling down is negative. And how much higher does it go above the bat that hit it? So here's where you have to kind of steal some information. We know that at the peak, at that instant, it's not going up or down. So at that instant, its final velocity is 0. Not ever, but for the segment we're analyzing, up to the peak. So we just kind of stole this piece of information. The final velocity is 0. And we want to find, first, part A, how much higher does it go? Well, in terms of our equation variables, that's D. So this specific combination of variables, we can connect with VF squared equals VI squared plus 2AD. So we're going to have 0 equals 625 minus 19.6D. Add 19.6D to both sides. So 19.6D equals 625. Divide both sides by 19.6. And the displacement, or how much higher it goes, is going to be approximately 31.9 meters. So that's part A. And then in part B, how long does it take the ball to reach its peak? So that's time. So rather than rewrite all the same given information and everything, we can just kind of do something like this. You can just kind of draw a little bracket to show all this information and kind of show that we're continuing with it over here. And we're trying to find, in this case, time. So this combination of variables, we can tie together with VF equals VI plus AT. So if I subtract 25 from both sides, negative 25 equals negative 9.8t. Divide both sides by negative 9.8. And notice by being consistent with signs here, we're going to end up with a positive value of time, which we should get. So about 2.6 seconds. Okay, now taking a look at number 19. A kangaroo jumps to a vertical height of 2.6 meters. How long was the kangaroo in the air before returning to the ground? So notice this really is similar to the scenario that we just analyzed, but instead of being a ball, it's a kangaroo. So just obviously a very superficial change, but we are focusing on something different. how long was the kangaroo in the air before returning to the ground. So in this case, we do actually want to know the total time up and the total, and the total time down put together. So we can go about this a couple different ways. Because of the symmetry of motion, you can analyze the way up to the peak to get the time and then double it, or you can just straight up analyze the whole time. So you have some choices there. But again, that's why it's important to decide for yourself, and also in terms of documenting your work. With the more complex motion, like something moving up and down, while there's a greater variety of ways to analyze it, there's also a greater variety of ways that you can kind of mix some things up if you start combining pieces of information about the whole trip with just analyzing up to the peak. So you got to make sure you're mindful of that for yourself, and then also in terms of how you document it. So in this particular case here, I'm just going to analyze up to the peak. But because it didn't have to be done that way necessarily, you have to go out of your way to say that's what you're doing. So given information, let's see what we know here. So the vertical height of 2.6 meters, well, in terms of our equation variables, that's displacement. So the kangaroo goes up 2.6 meters. The entire time it's on the way up, gravity's pulling down, negative 9.8 meters per second squared. Notice we're being consistent with our signs for these vectors. The kangaroo going up, being positive, is a positive displacement, and gravity pulling down is negative. And again, we can steal a piece of information. When the kangaroo's at that peak height, at that instant, it's not moving up or down, so final velocity is 0. And then we can find, we're looking for time. Now, we've got a couple different ways we can go about this here. But I'm gonna show one way to do it that's not necessarily the most efficient way to go, but along the lines of showing how you can connect these problems in a variety of ways. So what I'm actually going to do is figure out what the initial velocity of the kangaroo is, and then use that to get the time. So I'm going to do VF squared equals VI squared plus 2AD. So 0 equals VI squared so we have 0 equals VI squared minus 50.96 approximately. So bring it over to the other side. Take the square root of both sides. So the initial velocity of the kangaroo to get up to a height of 2.6 meters ends up being about 7.1 meters per second. And now that we know that, we can take that value and use that as a new piece of information that we didn't originally know, and now combine with the other things that we know. We can do VF equals VI plus AT. So 0 is approximately equal to 7.1 minus 9.8t. Add 9.8t to both sides. Divide both sides by 9.8. So the time up to the peak ends up being about 0.73 seconds. Now, you got to keep your eye on the prize. That's the time up to the peak, but that's not the question that was asked. It could have been, but it wasn't. The question was, how long was the kangaroo in the air before returning to the ground? So we want the whole time. So along the lines of documenting the work, you can just do something like this. Let's label this up to the peak. So then you can kind of just do times 2 and then kind of put a little note in parentheses, time up equals time down, just to show that you're applying that concept of symmetry of motion. So we've got about 1.46 seconds. All right, Raiders, that's it for now. Continue on later. As always, if you have a question, contact me on the Remind app.